energy, this name is from this paper, Graduate Inflation in University of John, from 1990s, okay? So, basically we applied what he has done 30 years ago, 33 years ago, and I was so we applied same thing to the late universe, okay? But the difference is that we allow it to get negative energy density values. At that time, if you read that paper, they do everything to avoid negative dark energies, okay? And for instance, if here, this small lowercase lambda is 1/2, for instance, then you have viscosity. So this, let me first tell you what's this. So in general relativity, from Bianchi identity, we have conservation of T mu, but we cosmologists usually see this equation, continuity equation. Theta here is 3h, okay? So here, this Barrow is equal to rho plus p. Okay, we cosmologists almost never see this equation in our papers because this is the energy conservation equation. This is momentum conservation equation. This d mu is special gradient of pressure, and Barrow is rho plus p. Mu dot is acceleration for acceleration. So this is basically Newton's second law of motion. Because if you have gradient in pressure, so it's like force, right? So you get acceleration. That rho is inertial mass density. So the interesting thing is this: if you think about usual vacuum energy density of quantum field theory, it is exactly equal to 0. So what we are discussing is this. Instead of maybe inertial mass density is more fundamental concept compared to energy density because instead of using energy density, if I use inertial mass density, I fully define vacuum energy, right? It's exactly 0. But we are going on that it's exactly 0. Maybe it is not 0, so we should check it by data. And Nihan will give a talk about that. Okay, so simplest deviation from 0 inertial mass density of vacuum energy may be a constant, non-zero, but constant vacuum energy density. Okay, we studied that case, but then John remembered that he has this graduated inflation universe using exactly the same thing. So this is the simplest dynamical deviation from the 0 inertial mass density of vacuum energy density. Okay, so interesting thing is this: when we solve these equations, they are quite nasty. We are getting this equation. So basically, graduated energy is this model in terms of inertial mass density. But if we write it in terms of rho energy density, we have this quite interesting equation. So this is very, very rich in showing very, very different behaviors. Okay, so then we notice that this rho changes sign at this ratio. Okay, psi is a constant from combination of gamma and lambda. Okay, so this graduated dark energy. Then at that time we were worrying about Lyman tension. Where was that? Yeah, okay. We were not thinking about H0. Okay, so we just noticed that it will also doing good things with H0. Then we constrain this model, okay? So the interesting thing is this: if this lambda power here is small, very close to 0, you don't get anything interesting. So you just get something very close to lambda CDM, okay? So, but interesting thing was this. So when we constrain this gamma and psi, so this side, this part is lambda CDM. When you go in this direction, you have lambda CDM. Okay. So when you go for large negative values of lambda, what happens is this. In this case, you see lambda CDM win the game. Okay, so you have this yellow, it is here. So this probability distribution, so it favors lambda CDM. Okay, so interesting thing is this. When you go to larger negative values of lambda, for instance, -2, it is -2, it is here, no? Okay, so let me continue, -4. Yeah, okay, the interesting thing, if you see -4, you see you have a new peak here. When you go for -6, we got this peak here. So this peak is larger than this lambda CDM side. Okay, so go to -10. Now we got the peak, now peak moves in this direction. Okay, so, but when we look at the side, what happens is this. Here we have lambda CDM for 0, lambda -2. Peak is still here at the lambda CDM. Notice this, we notice a new peak started to appear there, okay? So -4, you see this peak is larger than the peak of lambda CDM. Then, when we go to -6, we found new peak here. This new peak is here. Now we found that peak is getting larger and larger, but very stable at a certain position. That was very interesting. Then, we noticed that using combination of these, actually we were finding the redshift at which energy dynamics change sign. So you see it is very stable. Where once you go to the values less than -6, you find a side switch in energy density at a very stable redshift. Okay? So we can see the same thing here. Lambda is 0. Of maximum, we call it of, we have binomial distribution there. So at of maximum, this is lambda CDM. Where is the maximum? It is not there. So lambda -4, you see this new peak. Go to -10, wow, our new peak is here, detached from lambda CDM. If I go to larger negative values of lambda, you see the model prefers another model away from lambda CDM. So this is the concept when we allow lambda to be free parameter. So our new peak is still there. Now we notice that by chance, with this new peak, you see there is no contour here. So we have new contour within 1 sigma separate two contours, right? So but we have also larger H0. This we were not expecting because we were focused on Lyman-alpha. So here you see H0. So for the new maximum we have this. It is consistent with TRGB measurements. So this is lambda CDM side of the model, limit of the model. So lambda psi to the contours. Lambda CDM is top right here. So the thing is this: if we were not brave enough to deviate from lambda CDM a lot, so if we were using our price around somewhere here, we will think that okay, lambda CDM is favored. But we were brave enough. Then we moved this region. You see, when you are brave enough to count these interesting values, you have another region where all the parameters are very stable. Around lambda CDM, I mean, nothing is stable, but we are very stable here. And then, lambda CDM model, scientific cosmological constant model, is nothing but this place we focus on. So we say, okay, forget about this and study only this region. So that corresponds to this curve, you see. You drop here, edge drops, and go just through the middle of Lyman-alpha data. And the thing is this, I mean, instead of looking at all maximum, which is lambda CDM vicinity, and limit maximum is lambda CDM vicinity. So And then, because you have drop in HZ at for Z values larger than Z dagger, sign switch, to keep DMZ star, the common distance to the last scattering fixed, it's an integral, to compensate this drop for the gives you larger HZ for small Z values. For that reason, we are getting large H0. So, increase H0 constitutes with TRG. So, if you look at this figure, what you see here, a constant energy density up to this Z, this is Z star up to Z dagger. Okay, I mean, so you have a constant, almost cosmological constant here. It switches sign. And now you have negative cosmological constant. Why I say it switches sign? Look at the value, 0.75, minus 0.75. So if we make just sign switch, then I will just add one extra parameter to the ΛsCDM model. That's it. So we did it. So lambda goes to minus infinity limit is sign switch cosmological constant. This is signal function. So you have negative cosmological constant in the past. In the late universe, I mean, for Z at low redshift, you have positive cosmological constant. So solution of the exact solution. So instead of you have sine hyperbolic function, now you have sine function in the early universe. Okay. So then here we value guarantee that this model is consistent with CMB spectrum. In our preliminary investigations, we found this relation. You see, with respect to Z dagger, your H0 is increasing. So it shows me that if Z dagger can be like 1.7, we can reach the values consistent with Reyes measurement. Okay, and you can see similar things here. The good thing is here, you will not only reach the Reyes measurement, but also you will get, this is from using absolute magnitude, we can calculate absolute magnitude of supernovae. Okay, we did it. You see, these black ones for ΛsCDM, but these are for ΛsCDM. So it means that we solve H0 in this model, we automatically solve also ambitation. And also, you don't have any problem with Lyman-alpha data. For almost any values of Z, which is less than 2.3, the model always fit almost perfectly to the Lyman-alpha data. So you can get off from these three problems at once. So,
I'm sorry, but the Lyman-alpha data.
The tension is very small, 1.7 at the moment. Yeah, but at that time, where we started, it was like 2.2, 2.3. In
Which data set is this?
yeah, BAO, okay, sorry. So, yes.
Which year?
In the previous ones, it is 2014, so in the new slides, you will see new ones. Okay, new ones will come. Because, okay. So, I mean, the Lyman-alpha is not the main thing here. We started with Lyman-alpha, then we noticed that there are some more important things, okay? So from CMB analyzers, you see this behavior. So the thing is this, when we put BAO data, this data point here doesn't allow model to go those small Z dagger values, okay? But you see, the model is able to give values from shoes, okay? So the point is this: there is degeneracy between H0 and Z dagger. This is from analyzers. There is degeneracy between H0 and Z dagger. So we need to break that degeneracy, and we are doing it by using BAO data. Then we notice that for this is. If you use BAO data, the model reach to TRGB value, then notice this, it also gives you smaller values of SA. So this is also a good sign. And this calculation of MB is also going in the right direction. That's also good. So then, in another paper, the new one, we restudied model. Instead of breaking degeneracy between H0 and MB using BAO data, we tried to break it by using BAO, but we will do something within the and Pantheon data. So here are the constraints. So CMB+Pantheon, so it is here, not their constraint, but in case you have CMB+Pan+Ly-α, you have a tail here, okay? So, but when you include BAO, okay, we have peak here, but this peak is larger. But when we introduce MB prior, you see, we have very stable value for Z dagger, very well constrained Z dagger. We have tail here, we can discuss it later on. But again, when we introduce BAO full BAO data in the analysis, we are getting a tail, but now the peak is still here, around 2. So, very quickly, what happens? With CMB+Pantheon, you have Z dagger larger than 1.8, and with Pantheon larger than 2.2. If you use full BAO data, you have this is up 2 larger than 2.1. But what we need to have something like around 1.8. Okay. So S8 is smaller, you see. That's the good sign. So this is Bayesian evidence difference. So for instance, in this case, Bayesian evidence is like strong evidence, like moderate evidence in favor of ΛsCDM. But when we include BAO data, you are not able to distinguish between two models. But when we include MB prior, you see evidence goes to 12. So now we have strong evidence in favor of ΛsCDM, scientific model. So no MB tension, where is it? Yeah, okay, here. No MB tension, the Z dagger is 1.8, no H0 tension, no S8 tension here. So I put here, so 0 means better, right? I should, okay, this should be maybe here, but in that case we couldn't see this. Okay, so there's concept here. Okay, so we have strong evidence in favor of ΛsCDM in this case. So we know Pantheon plus sample is close related to Pantheon data plus MD prior. So we will move to that case. So here you see this. Okay, 5 minutes are fine. So you see H0. The good thing is here, when Z dagger approaches 1.8, you see everything goes in the right direction. So H0. So let me see. Yeah, this yellow contours in the lower panel. So you see it is just there, and MB is there. S8 is there in the right place. This is about ΛsCDM data. So this, this gray ones are for ΛsCDM. Okay. So some other parameters T0, H of the universe. You see, this is the H of the universe obtained from all Ozgur clusters. So we exactly predict the same H of the universe that is predicted and almost exactly the same from all Ozgur clusters. So, and there are some other things, I won't talk about that. So if you look at this table, you see, here, this one, you don't have any tension. Only in case, if we include BAO data, we need the model step back a little bit, okay? So, let me skip this. So then we investigated in details the BAO data. We noticed that the model has problem only with low redshift BAO data, okay? So in that case, we could do two things. First, we can add a middle on top of scientific lambda. But in that case, you will have extra free parameters, which is not good. Or, instead of using 3D BAO data, another option is to use 2D BAO data, which is less model dependent. So, in the recent work, which is under preparation, okay, we will use Planck data, BAO transversal data to the BAO data, Pantheon plus with shoes and without shoes. So this is the situation with SA. You see the model was injected in the SA contour. This is for ΛsCDM, this is for ЛsCDM. This is baryon figure. In our case, you see the model goes into the one sigma contour. Okay, so this is when we use more data. This is here, so here you can see how when we change the data points, it becomes very stable, perfect. I mean, 2 minutes will be enough. So this is plot for H0. You see it is the one we predicted just in the middle of shoes measurement. So here is the summary. And so these black ones are for ΛsCDM. So this is the full data case. So no tension at all with MB measurement, no tension with shoes measurement. In SA also we don't have any tension. So here is the figure. But look at this Bayesian evidence difference. It is almost 20. And this model has only one free parameter. And basically, I think we have understood how to get from that one as well. So we can decrease number of free parameters to 6. At that Bayesian evidence will maybe 21, 20, so something like that. With only 6 parameters. But we have a very simple model. Just before Z dagger and after Z dagger, you have exactly ΛsCDM. Nothing else. Just you have negative correlation constant in the past. The model is exactly ΛsCDM. Just lambda has different values before and after Z dagger. So very simple model. So you have this Bayesian evidence difference, and this is the highest Bayesian evidence difference in the literature as much as I know, and my colleagues know. Okay, so I want to show this as well. So Z dagger is 1.7. So we have a very strong constraint here. And when we do this, we solve, I don't know, at least it seems that we are very good at solving these tensions simultaneously. Okay? But you can ask it. Okay, so when you solve, take care of this thing, are you working some other things? No. Because all these parameters are very rare, and T0 is slightly smaller, but this is almost exactly the same with global clusters. YT, BBN, we check that, BBN it is consistent with standard BBN because we don't touch the early universe, the combination universe is the same. So you see there is no tension. The major ones are first three. So there are some others, but they are more maybe controversial, but these first three are there, you see. And finally, this is the comparison between ΛsCDM and ΛsCDM. So green one is ΛsCDM and purple, it is ΛsCDM. So in the common three parameters, they are touching each other, okay, overlapping. But when you look at the right parameter, they are completely different. So this is the ΛsCDM. So you see when we add new data sets, the parameters contours are moving in different directions. Okay? And sometimes they move in opposite directions. So okay, it's a signal of some tensions. But when you look at ЛsCDM, in free parameters, in the baseline free parameters, when you add new data, these are not moving from their places. They are still just there. I mean, adding new data doesn't change anything in the baseline free parameters. And in the right parameters, where we add clean data sets, just we are converging to one point A in Z dagger. So, yeah, let me stop here. So, this is called ΛsCDM. Thank you very much.
Questions? Please, Salvatore.
Sorry. Okay, thank you. Very simple question. At the beginning, you defined a potential C. At the very beginning of your presentation.
Potential?
Yeah, when you give the Barrow object,
This?
okay, this one. This sign defined there could be yes, exactly.
Yes.
Be defined also in modified gravity or not, or is it?
Good. Good. I didn't tell you that. We have a theory, enlargement squared gravity, and we introduced that model to the literature together with Nihan, John D. Barrow, and me at the same time. Then we continued together. And this projected dark energy stopped with that because in one of our papers, which was logarithmic enlargement squared gravity, we found some new terms in the Einstein field equations. And the interesting thing was that these new terms were effectively resembling a source with a constant inertial mass density. Okay, then we talked with John. Now let's do it in GR. Okay, and this is the beginning of everything. Then we said no. So if we will do constant, we can go for minimal dynamical deviation. That is, that was the origin. So you
specifically it can represent some
perfect. Yeah, exactly.
Part of degrees of freedom.
Yes. That was very nice question because I was not able to talk about physics. This is already start from modified gravity. For that reason, if we can convince the communities how it works, I think the best thing is to look for such behaviors from modified gravity because having negative dark energy in GR is, I don't know how to defend it. Okay, but from modified gravities, no problem. So, thank you for the question.
Yeah. So it's good that we are on this slide. That lambda there is the parameters and it turned out. Oh, can you go back to the slide? Yes.
This?
That one, yeah. So horizontal axis, that's lambda, right?
That is? Okay, yes.
So
Yeah.
you can see it's completely unconstrained by your data. Completely.
This?
Yes. That parameter lambda.
Yes, it's true.
Okay. And so the laminar of the data that you mentioned, there was a follow-up to the 2014 result. Which follow-up is that? Laminar sign switching of lambda happened. The first result of there was a sign switching. That's a 2014 result.
Yes.
You mentioned there was a follow-up. There were more data.
Because this paper is from 2019.
That's not a data analysis paper.
This is the first paper. It has two parts: theory part, and in the second part we have data analysis. All these are in the same paper.
So SDSS?
Yeah, these are data from SDSS.
Which
No. These are from, I don't know, 2014, right? Yeah. So,
PR14?
yeah, they are 14. Yeah,
Who was
okay.
first author, please? Just quickly. Who was first author on that paper? Please. I'm done.
So just let me tell you
Okay,
this.
so-
This one answer to question. This you see this gamma. You said it is complete concept, but it is why. This is why. If you reach to -6, you have already get a shape like this. From -6 to -infinity, you just make these parts here more 90 degrees. Nothing changes. So basically when you go to more negative volume, you get this switch behavior more like abruptly. So basically it doesn't matter if after -200, -200, 2000 will not make any difference. Okay?
If you want to continue, this question after. Okay. So thanks also.